Hello. Okay, so good morning, everyone. Let's start our class today. There's some problem with the AirPlay, so I changed back to the desktop. I don't know why the screen doesn't work. It doesn't show the code for the AirPlay, but yeah, doesn't matter. We can keep as previously working on this desktop. And let me first find the PPT today. Yeah, also, first I want to inform you something like, yeah, the presentation, I mean, the PDF file of the lecture note has already been uploaded in the OLE. And also the link for the lab for submission is already released. The deadline is still next Monday, 17th of February. Okay, so today we are going to talk about the second part of the supervised learning. So we are going to talk about some other models of machine learning. And so in total, we are going to talk about 3 different models this class. The first one is the logistic regression, which is used for binary classification. And another 2 is called key nearest neighbors, KNN, and naive Bayes. Okay. And let's start with the logistic regression first. So from last class, we've already learned about linear regression, and logistic regression is actually based on linear regression. And linear regression, we are predicting some values. So it should be a real number. It should be a real number, such as prediction of housing price. And then it also has 2 assumptions. So first, the input data, or we see the features, and the output data, the target, have a linear relationship between each other. And also, the random noise has a normal distribution. Yeah. Let me see if I can use the pad here. So let's see, we have axis, right? And as we talked about last time, we will have some data point to fit. Let's say these are our data. And we fit it with a line with the linear regression. So you can see like all the data is not actually on, I mean, some of the data is not actually on the line that we fitted, the function that we calculated. It is not on the line. So actually there is some difference, still some distance between the point and the function. And because the data point have some random noise, but the point here is that the noise should have a normal distribution. So most of the data points will be close to this line. So if you find like some situation that all the data is like separate like this, then you cannot use a linear regression to fit the data. Yeah, so this is the point here. And then let's talk about the logistic regression. Let's talk about the logistic regression. So logistic regression predict the output which in a categorical value. So it is used for classification. That's why the output is a categorical value, okay? And it is discrete. So prediction, like linear regression, is predicting a real value and it is continuous. The value should be continuous. And then for classification tasks, the output is usually discrete. So this point we've already talked about in the first lecture, I think. Yeah. So it's like prediction of diabetes in patients, something like this. So the most important thing in logistic regression is like it estimates the probability of a class. So it decides which class it belongs to based on the probability it calculated. So this is how classification task is done, okay? And yeah, so in this logistic regression, we'll use an activation function called sigmoid activation function. We need to clean it, sorry. Terminate. You don't know how to use the tools here. I just delete it, right? Clear all my drawing there. Okay. Okay, so then let's talk about sigmoid function. So it's called the activation function. So there are various activation functions in machine learning, and this is one of them. And different activation functions, they have different, they are used in different cases, okay? And we are going to talk about other activation functions, but today we are going to talk about the sigmoid function first. So activation function is usually used to introduce some non-linearity to the model, okay? Because in the real world, most of the case, there are no linear relationship between the input and the output. That's why we need to put some functions or other things which can introduce some non-linearity into the model, okay? And so this is the formula of the sigmoid function here. This is the formula of the sigmoid function. It is quite tough to use this pen. Let's see. So last time, actually, we've already talked about the linear regression. And if you still remember, the function of linear regression that we used as an example is like this. So we have theta 0, y equal to theta 0 plus theta 1 x, right? So this is the assumption function that we used in our case. And then we just replace it we just put this y here, okay? So we use this one. So this is actually y. So y can be written as this format in the matrix format. Always this is y. Y equal to this one, okay? And maybe I can use this pen. That doesn't work. Okay, and so here you can see there is a x0, x theta 0, x0. So actually this x0, if you still remember that we talked about last class, x0 is equal to 1. So the first term here is actually equal to theta 0. Okay, so the first term here is actually equal to theta 0. So the example that we used in our previous class is just like this part. Let me first clean it. It's just like this part. this is the part of the function that we used in our previous class. And this is actually equal to y. Y equal to this is the function that we use. Okay, so or the fx we use. And now, when we are using this sigmoid function, we just put this function fx into the hx here. Okay, so this part is equal to this fx. We put inside, and then we map it to probabilities. So the main idea of using sigmoid function here is that we want to map this predictive value. We want to make this fx into probabilities. And then according to the probabilities, we can decide which class it represents. Where's my mouse? Okay, so yeah, that's I've talked about here. So logistic regression is used to estimate the probability of the class. So, and then what we are doing here using this sigmoid function is to map this predicted value into probabilities. Then according to the probabilities of different classes, we can know which class the input should be. Okay, and then here is the plotting of this sigmoid function. And so yeah, the point here is that this is 0, okay? The original point is here. This is 0 point, okay? So it mapped the function, the value from here to here, okay? So this is, here's 1, here's 0. And when it has one input, always see the fx. Fx is this part, okay? Is this part. When fx is a very big value, let's say 5 here, then the corresponding value in this after the sigmoid function is almost 1. So it has a very high probability of being the class of 1. And then if the value is very small, then the probability will be close to 0. Okay. So this is how it mapped the input to another nonlinear relationship. Okay, and then here we use a threshold value. We can use a threshold value. Okay. We can use a threshold value here. Usually we set as 0.5. And then if the probability is over 0.5, then it belongs to this class, the class 1. So this is the point. This is the threshold. This is the threshold. So all this part will be treated as class 1, and then this part will be treated as class 0. So logistic regression is used to solve binary classification, okay? So we only have 2 classes in this problem. So it can either be 0 or 1. And then that's why we divide it into 2 regions. Yeah. So according to the threshold and the probability, we can decide which class the input belongs to. Okay, then let's move on. So yeah, here we have example. Yeah, I'm just checking if that's the screen is sharing. Okay, so here we have example. So let's see. Yeah, there are a couple of students, right? And then some students passed the exam, and sometimes students failed the exam. And then the students who failed the exam is represented by the red points here. And the students who passed the exam is represented by the blue points here. Okay, and then we would like to do a classification based on the data to decide like which part of if you have a new data, we want to know like the new students is possibly to pass the exam or fail the exam. And then we need to find the boundary of these two groups of data. So in our linear regression, we are finding a line to fit the data, right? We're finding a line to fit the data I want. We have some data here. And in linear regression, what we are doing is to fit this data. And in logistic regression, it's a bit different. We want to fit the boundary. We want to find out the boundary, like the boundary of these two groups of data. And then we find a line to fit this boundary to split the two data groups. So this is what logistic regression is doing. Okay, and then in this example, we can see like it's plotting about the sleeping hours that students slept, and the hours students studies. So in this plotting, we can see that usually students study more and sleep more has higher possibility to pass the course. Right, so it doesn't matter that you don't sleep, you just study that you will have better performance in the class. Yeah, so yeah, this is the regime. And yeah, good strategy is that you can sleep in the lecture and then you can study while you are sleeping, right? So you increase the value of both axes. And then there will be some points here of the blue dots. Okay, yeah, so then let's go ahead. So here's a summarize about the steps. So firstly, we compute the weighted output using the linear model equation. And so we're still using the first part is still very similar with linear regression. We use a linear model equation, okay? This is called assumption function. And then we use a sigmoid function in the end of this linear regression to map the output of the linear model into probabilities value. And then we calculate the cross entropy. Cross entropy we'll talk about later. It's another loss function, different with the MSE, the mean squared error that we used last time is different, okay? And then we use this cross entropy to predict the output. And then update the coefficients iteratively by gradient descent, as we did last time. These last two steps are the same, okay? We are using the gradient descent to find the optimization value of the parameters. Yeah, so this is how logistic regression works. Okay, then here I'd like to talk about the cross entropy loss function. So again, here it's a cost function, but it's the same as loss function, okay? Loss function. So in this case, we will use cross entropy instead of use MSE. MSE is the mean squared error that we used last class, okay? And this time we are going to use this one, cross entropy. So actually the cross entropy formula should be like this. The loss should be like this. Minus y log, okay? Disappear. Wait. Target. Log H theta x s 1 log. Okay, yeah. So this is the formula of the cross entropy loss function. And so this is original formula. However, that we are doing binary classification here. So y, obviously the the target value, it can only be 0 or 1. Okay, the target value can only be 0 or 1. So when it is 1, then this term disappeared, right? This term disappeared. When the y equal to 1, this term becomes 0. So we only have the term here. Okay, and because y is 1, so y can also be eliminated. So it will be something like this. And then if y is 0, or the target value is 0, then this term, the first term here, disappeared because y is 0. And this term becomes to 1. And then we only need this term. And then it will be something like this. So this is the function, the formula of the cross entropy loss. And so, yeah, the curve of this loss will be something like this. So it is a smooth monotonic functions. So it will be easier to calculate the gradient of the functions, right? So it's always increasing or always decreasing. So then the other hash. And so, yeah, it make it easy to calculate the gradient and minimize the cost. So this is the introduction of the cross entropy loss. And then I'd like to talk about why we need to use cross entropy loss in this case. And yeah, so let's say if we are still using MSE, okay. So these two cases we are going to talk about is linear model, linear function, plus sigmoid function plus the loss function. So for loss function in this comparison, we will have MSE and the cross entropy, CE. Okay, cross entropy is called CE. Okay, so the first two parts we're using the same. The assumption function is a linear function, and the activation function is a sigmoid function. Then we compare the performance of MSE and CE in loss function. And then let's say if we have a target of t equal to 1, and then we have a prediction of f theta equal to 001. Yeah. Sorry, there's a mistake. This should be hx. hx, okay. Please pay attention here. This should be hx. This is the final output, h theta x of the sigmoid function. Okay. And then if our h theta x is equal to 0.01, the MSE will be, how we calculate the MSE? Do you remember? MSE is like the target T. We calculate the distance between the target and h theta x, the output. And then we squared it, right? So this is how we calculate the MSE. So if see we only have one point here. And then if the h theta is 0.01 and the t is 1, then we got a loss value of how much? 0.98, I think. Let me calculate. Yeah, 0.98. And then if we calculate the loss of when the output is 0.001, we will find this loss function. The loss is still using this formula here, okay? And then it will be like 0.99, I think. Yeah, 0.998, something like this. 0.998. So we can see the difference between this loss and this loss is very small. So the model will think there are no big difference between these two loss, and the gradient, the gradient will be very small. So when the gradient is very small, then the model will converge slower. So that's why it doesn't good when we are doing training, because the difference between the two loss is too small, and it's not a proper way to do the training with this loss function. That's why we use cross entropy. So when we are using cross entropy, CE here, okay? If we're still using the 0.01 and 1 as example, so the output is 0.01 and the target value is 1, then the loss will be 2. And then if the input or the output is 0.001 and then the target is still 1, then the loss will be 3. So we can see then, in this case, these two loss will have a much bigger difference. So it's better for the training process when using the cross entropy loss. And there are also some other reasons, but I'm not going to talk about the details. It is more complicated in the mathematicals. In the mathematics. So this is not going to be, sorry. Yeah, we are not going to talk about it. So the point here is like in MSE, we will have a lot of different local minima. So it's very tough to find the global minima, the best options. So usually the model will converge in a local minima. Yeah, in the linear, in the logistic regression. Okay. So that's why we don't use MSE. This is another disadvantage of MSE in this case. You just need to know this, like it has a non-convexity. Okay, you don't need to fully understand the underlying mathematics of these characteristics. Okay. Yeah, so this is why we use cross entropy. Okay. But if you are calculating the gradient of the logistic regression with the sigmoid function, you will find that the formula here is the same with the formula that we talked about in linear regression. So they have the same partial derivative, okay, with the linear function or with the linear regression model. And yeah, so if you still remember, just a minute ago, I've said that the gradient of using MSE is very small when output is an extremely small number. But now I said that the gradients are the same. So what's the difference here? Why I say these gradients are the same. So in this case, we are used a linear function with a sigmoid activation function. We are talking about the combination of these two, okay? Then we need to use cross entropy loss. But when I'm saying that the partial derivative of the sigmoid, what's the name? The logistic regression. When I'm saying that the partial derivative or the gradient of the logistic regression is the same as the MSE partial derivative, we're talking about different models. So this is a comparison between two models. One is the linear function fx plus sigmoid. And then the competitor here is the linear function alone, right? Linear function. This is plus CE, the cross entropy. And the competitor is the linear function plus MSE. Okay. So you can see here we are compared with linear function plus MSE, which is also called linear regression. And here, when we are talking about why we use cross entropy, we are talking about linear function plus sigmoid function. And then we change the last component of MSE and CE. And here in this linear regression, we don't have sigmoid function. That's why we use MSE. Okay, and then the gradient of these two functions, this and this, are the same. Okay, they have the same gradient formula. And if you are interested in the gradient function of this one, the linear, let me write it again. If you are interested in like the gradient of this linear function x plus sigmoid plus MSE, then it will be something like this. It will have one more term of 1 minus y. Okay, so it will have an extra term. It will have extra term like this in this. It will have extra term of this inside this. Okay, and then when we have this extra term in this partial derivative or in this gradient, we can say that either when the y value is this should be let's have different, wait a minute. Because sometimes we use Y, sometimes we use different. Okay, just let me write it again. We have a new term. So in this case, it should be 1 minus h theta x. Like this, h theta x. So we have an extra term like this in this loss function, also in this gradient function. And then we can see when theta x is very small or very big, the gradient will be very small. So let's say the theta x is 0.001, and then this term will be very small. So the gradient will be very small. Or either this term is like h theta is like 0.99, because here and this will become 0.01. And again, this term will be a very small number, and then it will influence the whole value of this gradient, which makes the gradient very small. Okay, so this is why we cannot use linear function plus sigmoid plus MSE. In this case, we need to use cross entropy instead of MSE. Okay. Yeah, and the update rule is also the same as previously, the one we talked about in the previous class, the update rule. So alpha here is the learning rate. And this is the parameter, the group of parameter in the previous step. And then theta j is the parameter in the current step. And the current step, or we see the next step and the current step, doesn't matter. Okay, so I will say, yes, to be more clear, we can see theta j is the parameter for the next step. And then here, this theta j is the parameter of the previous step. So we can put like this, theta, we can put the hat here, okay. So just see this is two different, but in the coding, they are the same, okay. But in mathematic way, we need to distinguish them. And yeah, so just like theta, the next theta j is equal to the current theta j minus the learning rate multiply the gradient. Okay, so this is update rule that we've already talked about in the previous class. And then another thing is quite important here is the evaluation of the model. So in the classification task, how we evaluate if the model is working well or not. So usually we'll use the accuracy that you might be quite familiar about this accuracy. But then like for all the instance here, we can have a confusion matrix. So confusion matrix show how the model confuse the samples. I mean, how the samples confuse the models. So how the model make mistakes and how the model, what kind of correct prediction the model made and what kind of false, incorrect prediction by the model, like this. Show the number of correct and incorrect predictions made by the classification model. Or we see the classifier. And then we can use the coronavirus or the COVID, we see the COVID as an example. So let's see, in total, we have 10,000 people. We have 10,000 cases. And then we want to test them if they have COVID. Okay, so let's assume that only 100 of them is patient of COVID. Okay, and then we need to do a binary classification. So the binary classification here means the patient could either be positive or negative. So positive means they got coronavirus, they got COVID, and then negative means they don't have. Okay. And here we have a confusion matrix. So we will have positive cases and negative cases. And then we also did some predictions. So sometimes we predicted negative, sometimes we predicted positive. So because the accuracy is not 100, so the predicted negative is different with the true negative cases, right? So sometimes you predict someone doesn't have COVID, but actually the guy might have COVID. So if you are doing like this, so someone you predict as negative, but actually it is positive. So it means false negative or false negative here. Okay, false negative. So it means, hey, my writing is so shit. Okay. So it means like the case is positive. So the true case is positive, but you predict as negative. And then it means false negative. Okay. And then in this case, you predict as positive. But the true case is negative. Then it means false positive. So it's quite confusion matrix is quite confusing. Okay. So this is false positive. And then if you predict it as negative, and then the true case is also negative, then it means true negative. True negative. And also here, the last one is here. True positive means your prediction is positive, and then the true cases is also positive, which means you are correct. It means true positive. So we can see here that true negative, I'll give a star here. True negative and the true positive means that you are doing correct classification. And then the false positive and the false negative is the mistake you made. Not you made, the classifier made. Okay, so these are the mistakes. So to easier understand, every time you say false here, no matter it's false positive or false negative, it means the classifier made mistakes. And if you say true here, true positive and true negative means the classifier is correct. Okay. Yeah. And then in this case here, in this example, we have 60 true positive cases instance and 9,760 true negative cases. So if we are calculating the accuracy, we will see the accuracy is quite good. So it will be like 98.2%. So what is accuracy? Accuracy is just all the true value, you put it together. You do summation of the true values. And then here is actually the total data set. The total samples you have is the summation of all the samples here. So this is actually the true. True is TRUE, right? True minus all, true over all. Okay, so this is accuracy. Because this formula is quite complicated, but you can understand as true over all. So it is accuracy. So we can see in this case, the accuracy is very high. So is this good? Might not be. So I can give you a easy understanding example. how to say, actually, I want to write, but my pad doesn't work. I mean, the AirPlay doesn't work here. So let's see. We can create a new slide. Okay, we write on this new slide. So I just want to explain why sometimes the accuracy is very, very high, but the model doesn't work well. Accuracy doesn't mean the model works well. So let's say you are taking, or your friend is taking a quiz or exam, okay? And I'll give him like 100. There are in total 100 true or false questions. In total, we have 100 true or false questions in this exam, okay? This exam only have true or false questions, and it has 100 true or false questions. And your friend didn't study anything, so he doesn't know the answers. And his strategy is like, he will pick all the questions as false, okay? So your friend give all the questions false. Your friend. Let's say your friend's name is A, okay? Called little A. Is give 100 false for these 100 questions. And then you are studying quite well in this course, okay? Not perfect, but still quite well. That you got 80% correct answers. Okay, so I don't care like what answers you choose, but in the end you got 80% correct answers. But sometimes the teacher like me is an idiot. Okay, so when I design the questions, these 100 questions, there are 99 questions whose answer is false, and only one question whose answer is true. And then you can see here, your friends doesn't know anything about this course, but he choose all the questions as false, and then he got 99% accuracy, right? And however, you study this course quite well, but still you make 20% mistake, and in the end you got 80% accuracy. So you can see your friends who doesn't know anything about this course get better score than you. So does it mean your friend has better knowledge in this course? Of course, no. So why this situation happened? Because the samples of the classes are not balanced. Okay. So if I have 50% answers, which I'm spelling the false correctly, right? False. I think correct, doesn't matter. Okay. If I have 50 questions false and 50 questions true, it means the answers are balanced. Then your friend will only have 50% accuracy. And then your accuracy is better than him. So this means when we are using accuracy to evaluate the model, it only works when we have a balanced data set. So if the data set is not balanced, I mean the classes in the data set is not balanced, then accuracy, okay, then accuracy doesn't work anymore. It cannot give you the correct evaluation of your model. Yeah, so that's why we cannot use only accuracy in the models, because usually the samples of the model would be not perfectly the same. The samples of different classes will not be perfectly the same. So that's why we need to introduce some other performance metrics. We need to introduce some other performance metrics like this, where we're talking about, like precision and recall rate. Okay. So precision means, when we are talking about precision, we are only focused on the TP and FP. So we only focus on this column. Okay. So when we are calculating on this column, it means precision. And the formula is here. You can have a look. Okay. TP over FP plus TP. TP over FT, FP plus TP. So it's like this column. And we were talking about recall rate or the sensitivity. We focus on this row. So this row means recall rate. Okay. Yeah. And then let's use this example. Here, when we calculate the precision, we have only 30%. So it's like when precision means like this row, right? This is only 30%. It means the true positive over all the positive values. Yeah. So if you put them together, so it's like TP. TP over FP plus TP, right? And then if you combine this F and the T together, then you will see like this can be simplified into TP over all P, right? So it's like the rate of true positive over all the positive. This is the precision. And then for recall rate, it's like in all the predictions, in all the true positive cases and false negative cases. Yeah, this is actually, I don't have a more concrete description of recall rate, but yeah, it's focusing on like the false negative compared with precision. It focuses on false negative rate. So it's tell you how much false negative rate it has. When the false negative rate is higher, then the recall rate is lower. And false negative means it is positive, but you predict it as negative. Okay. And then I will give you some example of how the difference about precision and recall rate. So let's see. We have like some people, some patient may got cancer, coronavirus, doesn't matter, right? So in this case, we still use the coronavirus, the COVID example. So actually, when you are doing some diagnosis for the patient, you can bear that the patient, you can bear in this situation that the patient actually doesn't have COVID. And then you predicted him that he has COVID. So it's not a big problem. You can just test again, right? So you don't really care about these mistakes. However, if the patient really have COVID, but you predicted him as healthy, then it causes a very big problem. So it means in this case, this false negative is more important. And this is usually the strategy we used in medical diagnosis, because you cannot bear any cases of false negative. So if the patient have some disease, you must diagnose him that he has this disease. But if the patient is healthy, it doesn't matter. I mean, it not that serious. I mean, or not that severe that you diagnose a health patient as have some disease. Okay, because if you tell like someone have some disease, he will, of course, going to check in some other hospitals, maybe check for several times to make sure he really got this disease. But if you just give a diagnose that someone don't have COVID, then maybe, I mean, no one care about anymore. So that's why in medical diagnose, the false negative is more important. It also means the recall rate is more important than this precision. Yeah, so this is sometimes recall rate is more important and sometimes precision is more important, depend on your application. And then accuracy usually give you overall view of this performance of the model, but sometimes it is not quite reliable, and you need to calculate all these accuracy, precision, and recall rates to comprehensively evaluate your model. Yeah, so this is about the performance evaluation of a classifier. Yeah, and yeah, okay, so let's first have a rest of 10 minutes. Okay, thank you very much. And if you haven't take attendance, then you can take it here. Okay, so let's come back to the slides. And yeah, so first I want mention again about precision and recall rate, how to understand precision and recall rate. So actually there's another way to understand it. So like for precision, as I've talked, like you are focusing on this column, right? You're focusing on this column. So it actually means for all the predicted positive, for all the cases that you predicted as positive, how many correct cases there is. And then for recall rate, it's like for all the positive cases, for all the true positive cases. No, not true positive. So for all the positive, originally positive cases, I mean, the real positive cases. And how many samples that you classify correctly. So it's like how many samples you classified correctly over the whole number of positive cases. So when we're talking about recall rate, we're talking about the positive cases. And then when we're talking about precision, we're talking about the predicted positives. Okay. So it's like for precision, it focuses more on the correct rate of the predictions you've done. And for recall rate, it focuses on how many true positives you can find in the positive cases. Yeah. Okay, then, so actually there's a trade-off between precision and recall rate. Usually in the binary classification, when the precision is higher, the recall rate will be a bit smaller. And so usually there will be a trade-off. That is also what we've talked about, that in different applications, you might need to focus on different performance metrics. Sometimes you might need recall rate, sometimes you might need precision. Yeah, so there's a trade-off. Okay, then in logistic regression, we can also do regularization as linear regression. We've talked about in previous class. So the method is actually the same. So we just need to add one more term of like this in the loss function. Okay, we just put some regularization term as what we did in the linear regression. So they're actually the same to prevent the model from overfitting. Okay, regularization. And here are some typical applications for these two different models. So linear regression, usually we use for like financial forecasting, like the stock market, the price of the stock market. I mean, this is like a potential application, but usually we will not use this kind of single model, okay? Like in this kind of complicated tasks, usually we don't use linear regression, but if you say that linear regression can be used in these tasks, then it's also true. I mean, it is also correct because you can use, but might not get a very good performance. And also here are applications for logistic regression, and those are all classification tasks. So usually logistic regression can only used in binary classification, where you only have two different classes. But actually, if you do some modifications, you change some like the activation functions or change some structure of the logistic regression, then it can also be used in like multi-classes classification, like handwriting recognition. or like, yeah, geographic image processing and image segmentation, something like this. But yeah, still these two modules are very basic. So nowadays, usually we don't use these models for complicated tasks. Okay, then we've finished the logistic regression. Let's go ahead to the next one, KNN. It is called K nearest neighbors, KNN. K nearest neighbors. Usually it's referred here, it refers to KNN here. Okay, so these two models that we're going to talk about in the following time, the KNN and the naive Bayes are non-parametric models. So it means we're not going to learn the parameters of the model. What does it mean? So like previously, or in our model, we will have like a set of parameters, right? Theta 0, theta 1, theta 2. These thetas are all the parameters of the model, and these parameters are learned during the training. However, in this KNN and the naive Bayes, we will not have any parameters inside the model. So that's why it is called non-parametric model. Okay, and usually these days we use parametric model. Non-parametric model is not quite popular. And yeah, but K-nearest neighbor is still sometimes useful in some simple tasks. Okay. And then let me talk about what is KNN. So just like its name, it finds the near, it's doing classification based on the nearest samples. Okay, so let's see, we have two different classes here. We have two different classes. One is the red circles, another is the green squares. So there are two kind of classes. And then we have a new sample here. This is a new sample. We don't know which class it belongs to. And in KNN, what we do is that we calculate the distance between this sample, between this new sample to all other samples. Okay, so we calculate all the different distance here. We calculate all the distance. And then according to these 6 distances we have, we find the smallest value of the distance, which should be these 3, right? So how many, let's say like, for example, in this case, we can find that this star is closer to the red points here. And then we just classify this new sample, the star here, as the red circles. But there's one thing that we need to set, is the K. So the K here in KN refers to the number of nearest neighbors that we wish to take to vote from. Okay, so let's say in this case, if we set K as 3, KNN, this is K nearest neighbors, right? So K nearest neighbors. And if we set K as 3, it means 3 nearest neighbors. So we find the 3 nearest neighbors here. They are all the red dots here. So it belongs to the star belongs to the red dots, red circles. However, if we set K equal to 6, I mean, in binary classification, usually we use a odd number. We don't use a even number, okay? But just for example here. And then we can see if we use key as 6, we will find like 6 nearest neighbors. And then the 6 nearest neighbors contains all the points here. Then we don't know like which class this star belongs to, because we are going to use a majority vote. Majority vote. We can write here. Okay. By voting, okay, voting. So always say majority vote. 少数服从多数. So let's say like we have 3, if we are using key as 6, we have 3 points, 3 distance saying that this star belongs to these red points. And we also have 3 points, 3 distances saying that this point this point belongs to the green squares. Then we don't know which class this exactly belongs to. So if we set key as 6, then there will be a problem. And so that's why the point here is that we need to clearly, we need to tune this key. Like what the value should be. We need to tune this value to find the best value for classification. Like in this case, you can either use key as 1, 2, 3, 4, 5. They can all correctly classify this star as the red points. If you set key as 1, then it finds the 1 nearest neighbors, which should be this one. And then because this neighbor belongs to red points, so this star belongs to red points. So this is how it works. It's also like that, like in our class, we have level 3, year 3 students and year 4 students, and might be your friend would like to sit together with you, right? So if I'd like to know which year you are in, I just need to check the guy who sits beside you. And then if the guy sits beside you is from year 3, then you are more probably to be year 3 students because your friend is from year 3, right? So this is the idea of KNN. It find the data nearest to you. Like sometimes if I only find one friend, it might be not very calculate. So if like you sit with 4 different friends or 3 different friends, you sit together. Then if I check all these 3 friends of you are from year 3, then probably you are also from year 3. So this is how we adjusting the K value here, okay? So sometimes you use, if you just check once one neighbor, then it is not accurate. So you check more neighbors. But the problem is like if I increase the key value to very big, let's say I checked all our students here to see which year you are from, then it might be a problem because of course we have more year 4 students. And then the final decision will always be year 4 students, no matter where you sit, right? So that will increase the problem. That will give rise to a problem. So we need to tune this key value to find out the best value to decide, to know which year you're from. This is how we do KNN. Okay, and then the distance here is actually, the terminology is called Euclidean distance, 欧式距离. Okay, so it's just like the root square of the squared distance, like this. Yeah. Okay, let's go ahead. Yeah, this is what I said. You need to carefully choose the key value when you are doing the model, when you are using this KNN model. So firstly, you might use some some key value here. Let's say it is 5. And then you got some error, right? During your validation of the model, you will see, oh, you have 25% error. And then you increase the size, the value of k to 6, then you might find the error is decreasing. You only have 15% error, and then you increase the key value again. Let's say you use 9, and then you have less errors until you try the value of k here. Then you got the optimal k of this model. And when you increase, you will find that when you increase the key value, the error also increase. Then you will see also the optimal key value is somewhere near here. Okay, so this is how you tune this key value of k and n. You're using the validation error or validation accuracy. It depends what performance matrix you are using. You can also use like recall rate, precision that we've talked like in previous slides. Okay. Yeah. Oh, what I want to say, I forgot. Validation error. Sure. So yeah, doesn't matter. So it's how you choose the key value. Oh yeah, I remember it. So this is just example, okay? Yeah. So it's not means like always the key value should be like this. So this is just an example. And in your application, you need to do it by yourself to check what is the best key value. Yeah, and here's example. Another example of how we calculate, how we classify these things. So let's say we have data from a survey on special paper tissue. And then there are two features of this paper tissue. Okay. One is the acid durability. Another is the strength of the tissue. So we already have some data here. Like if we have acid durability of 7 seconds and the strength of 7, then we'll classify this tissue as bad. And sometimes, according to the feature, we'll classify this tissue as good. And then this is the data we already have. So we now have a new data. Yeah, so the new data has a feature of 3 and 7. Two feature, okay? The first feature is 3. The acid durability is 3, and then the strength is 7. And now you want to know if this new tissue belongs to good tissue or bad tissue. You just check the distance, the Euclidean distance between all other samples. So all other samples is the samples we have here, right? This is the original data set for our reference. And now we are going to use this original data set to decide which class this new sample should be. So we calculate distance. The distance from the first from the first sample is 16, second sample is 25, and also 9, 13. We have all the distance from all the samples we have in the training data set. Then we use this distance. We rank all the samples by the distance, right? So we can see this 9 is the nearest one. is the nearest one, the nearest point with the new point, which is 3, 3, and 7. So this is a new point, okay? New point we have is 3 and 7. And here, this 7, 7 actually means 7, 7. Okay, this is 7, 4. If you talking about it in the, oh, sorry, axis, coordinate axis, and this is their position. Okay. Then you react the distance. You find that this one is the smallest one. This one is the nearest one. So you say it is good. So this new instance may be good. But if we set the key nearest as 1, okay, if we set it as 1, then it is good. If we set it as 2, then we need to check the 2 nearest points. So it should be these 2. So we can still find that these 2 are all good. So this new tissue probably belongs to a good tissue. And then we increase again to 3. So this is the key value, okay? Key value. If we increase the key value to 3, then we need to check this one. This is the 3rd nearest neighbor. But this one is bad. However, it doesn't matter because we are using majority vote. We have in total 3 distances. 2 of them said this is good. So this new data point is still can be, the new data point can still be classified as good. Okay, yeah, this is the point here. And this is 1, 2, 3. And then if we don't set 4, then because this last one doesn't belong to the 3 nearest neighbors, so we don't need to consider it. Okay, unless if we set it as 4, the key equal to 4, then we need to also check this data point. What's the classification on this data point? Yeah. Okay. So there are some strengths and weakness of KNN. And the strength is like this robust to noise training data. Because you can set the key values to avoid to use the distance between the noise data. And then it is also effective and accurate when the training data is very large. Yeah, so all the model will be more effective and accurate if the training data size is larger. And the weakness is also very, very obvious because you need to calculate the distance of all data points in the data set, right? So no, if you have millions data, you need to calculate millions data set. You need to calculate millions distance among this data set, and then rank those million distance to find out the k nearest neighbors to decide which class it belongs to. So it is very, how to say it is difficult. The computation cost will be very high. Okay, so what I said is it means the computation cost is very high. So it will be very slow if the data set is very large. And also, it is always difficult to determine which is the most optimal metric for measuring the distance and which attributes to use to produce the best result. So KN is suitable for applications which sufficient domain knowledge is available. This knowledge about the selection of an appropriate doesn't matter. Okay. You can just ignore this one. Okay. So like the computation cost is very high. So this you need to remember. The KN's computation cost is very high. So usually when we are training model, the computation cost is usually during the training. But KN is different because it is non-parametric. So you don't need to actually perform the training process. You just need the data set. But every time it's doing classification, it needs to do all the calculations again. So this is why it is computation cost is very high. Okay, so this is about KN. We don't have a lot of time left, but yeah. So the last one is about the naive Bayes work. I'm sorry, naive Bayes classifier. And I think you've already learned about this formula or this model in other classes. So, and this model is actually not very popular these days. It's like, I mean, it's not because it's not that powerful anymore. So we don't use it very often. So because we don't have more time, so I'm not going through this classifier. And we are not going to examine this classifier, okay? We are not going to examine this one. Yeah, but if you are interested in this, you can have a look at this example here, okay? So then it's the end of this class. Thank you very much for your time and see you next week.